Alright class, so last time we started talking about bonding. The two topics that we talked about that you must know before we can move on was electronegativity, how powerful an atom is. We said some atoms are stronger than other atoms, and also valence electron. Those are the electron far away from the nucleus, so they can be involved in bonding. They can play around because they're not feeling the nucleus plus charge. Alright, now we're going to continue with that. Today we're going to talk about different types of bonding. We have ionic bonding, metallic bonding, and covalent bonding. Now, ionic bonding you already know. Always go back to the basics. Ionic bonding, when you have a metal and a non-metal together. When you have a metal and a non-metal together. Metallic bonding is when you have two metals together. Covalent compound is when you have two non-metal together. So always go back to the basics and you can never fail. Go back to the basics. Now, also for covalent bonding, I want you to remember now, and we're going to come back to this, that when you have a covalent bond, you can have two types of covalent bonding. You could have a polar covalent bonding, or you can have a non-polar covalent bond. And the polar has nothing to do with polar bear. It would have been cute if we had to do something with polar bear, but it does not. Still kind of nice and cool to learn about it. The first one is ionic. Now, we talked about ionic. You know ionic really well. We say ionic is a metal and a non-metal. And I need you to remember that ionic is balance of charges. Ionic is balance of charges. Don't forget that. Ionic is balance of charges. That's how you know it is balance of charges. Okay. Now, let me give you an example. Let's say if you have cesium and you have fluorine. Let's say you have cesium and you have fluorine. Okay? Now I want you to look at a periodic table. We talked about this last time. How many valence electrons does cesium have? Cesium has one valence electron. I'm just going to put a dot for a valence electron. Now look at the periodic table and look at fluorine. How many valence electron does it have? It has 7 valence electron, right? 1, 2, 3, 4, 5, 6, 7. All the halogens in group 7A, they have 7 valence electron. Okay, so cesium has 1 valence electron and fluorine has 7 valence electron. Now remember, cesium is a metal, fluorine is a non-metal. Now, fluorine, I looked this up, has an electronegativity of 4.0 and cesium has an electronegativity of 0.7. So which one is more electronegative? Cesium is the least electronegative atom on the periodic table. Fluorine is the most. So fluorine is a lot more electronegative. What does that mean? That means fluorine is a stronger atom. It's going to pull the electron toward itself. So it's going to grab the cesium's valence electron. So what I end up having is cesium is going to lose a valence electron. Now it's going to become positive because it lost an electron. And fluorine now is going to have 1, 2, 3, 4, 5, 6, 7, 8 because it got the valence electron from the cesium. And fluorine now is going to have a minus charge because it has extra electron. Now we learned this before, but now we can put it in perspective in terms of valence electron and electronegativity. Now what I call this 100% ionic. I call this 100% ionic. Now, why do I call this 100% ionic? Is because there is no sharing electrons. They're not sharing electrons whatsoever. Fluorine, high En value, is just going to grab that electron from the cesium and it's going to have 8 electrons now. So it's 100% ionic. There is no sharing going on. So far, so good. All right. Now, that was ionic. And metallic, we're not going to go over metallic in Chem 1A. I wanted you to know what the definition is. But metallic bonding, that's more for upper division chemistry classes. Now, let's go over covalent now. And I just misspelled it. Great. Let's go over covalent bonding now. Now, covalent bonding. So let's come back here. Ionic, we said, is a balance of charges, right? One lose, one gains. Now, if we go over covalent, what covalent bonding is basically sharing electron. What they do, they share electron. They share electron. Don't forget that. Now, we said if you have covalent bonding, you can either have polar covalent or you could have non-polar covalent. And let's go over what that means. Let's say I have hydrogen bonded to fluorine, okay? The EN value for fluorine is 4.0. The electronegativity value for hydrogen is 2.1, okay? Which one is more electronegative? You can tell me. Fluorine, right? Fluorine is more electronegative. Now, what does that mean? That means that fluorine is a stronger atom. It's going to pull the electron toward itself. So the way we show this, here is an arrow. The electrons are going towards fluorine. And I put a line at the end of this dipole arrow. So what I'm going to give this, I'm going to give fluorine a partial negative. You see this sign right here? That means partial. I'm going to give fluorine a partial negative. And what I'm going to do to hydrogen, I'm going to give hydrogen a partial positive. Why? Because, again, fluorine is going to attract most of the electron toward itself. So it's going to have more electron. But I'm going to give it a partial negative. Because hydrogen still gets some electrons, but not as much. Now, what we call this polar covalent. What do we call this? We call this polar covalent. Now, what does that mean? That means they are sharing, but they're not sharing equally. Sharing electrons unequally. They're not sharing equally. But they still share electron, just not equally. So they're still going to share electrons, but just not equally. Who has more of the electrons? The fluorine has more of the electrons. Are we good so far? So the fluorine has more of the electrons. Now, let's do another practice. Let's do another example. Let's say I have F2. Okay. F bonded to F. Now, EN value of F is 4.0. EN value of F is 4.0. You see where I'm going with that? Okay. So now these two atoms, they have the same EN value. If you have the same EN value, what kind of sharing would you do? You share electron, but it's going to be what? You share it equally, right? You share the electrons equally because they have the same EN value. They have the same strength. Whereas before, one atom, one guy had a higher EN value, so it would pull the electron towards itself. So covalent bonding, we can share equally. That would be non-polar covalent. That would be non-polar covalent. Or sometimes we can share not equally, and that would be polar. So when it's polar, it's polarized, is not shared equally. Non-polar, they're shared equally. Okay, now, we never think about this, but for a second, let's think about this. How would you draw ionic compounds? Drawing ionic compounds. Ionic compound, there's no sharing. It's just balance of charges, right? Have you thought about if you wanted to draw ionic compounds, how would you do it? For example, NaCl. It's pretty easy. Na is going to lose an valence electron, and Cl is going to get the electron. Na plus, Cl minus. let's say calcium fluoride, ionic compound. I have a calcium. Calcium is +2, and calcium has 2 fluorine attached to it, right? It's a balance of charges, the attraction of charges. That's what ionic compound is. So drawing ionic compound is kind of easy, you know? We have the charges and then they're going to be attracted to each other. Now, have you ever thought about how would you drawing covalent compound? How would you draw covalent compounds? They're sharing electron, sometimes equally, sometimes not equally, but they're sharing electrons. There are no charges going on. Now, to draw covalent compound is a lot harder because they're sharing electron. What we do, there's a system called Lewis structures. Lewis structures is for drawing covalent compound. Now, before we go over the Lewis structure, which will be our next lecture, bonding part 3, there is one more concept that you need to know. So you know valence electron so far for bonding. You know En value. There is one more thing to talk about, and that is Octet Rule. Now, CF, CF2, CF3, CF4. These are all covalent compounds. CF doesn't exist. CF2 doesn't exist. CF3 doesn't exist. CF4 exists. Why does CF4 exist? This covalent compound exists and the rest of them don't exist. It has to do with the Octet Rule. So the Octet Rule says you transfer for ionic compound or share for covalent compound electrons to form compounds to give atoms a stable electron configuration. And we briefly talked about this before. What is it considered stable electron configuration? Stable electron configuration means you have 8 valence electron. And why do you want 8 valence electron? Because guess who has 8 valence electron? Yeah, noble gases have 8 valence electron. Noble gases, they have 8 valence electron. And noble gases are considered sexy on a periodic table. Everyone wants to look like them. So that is our Octet Rule. You would only transfer a shared electron if you could form compounds to give atoms 8 valence electron. So we're going to come back here. This is the only one that it would give carbon 8 valence electron. The other one wouldn't, so they wouldn't form, and this one would be formed. All right, now I'm going to put up a table. Go to a new page if you don't have enough room for half a page. I'm going to put up a table here. And in this table, I'm going to put carbon, nitrogen, oxygen, fluorine, hydrogen, and boron. And on top, I'm going to write down number of valence electron and number of bonds. Okay, let's do this together. Let's do this quick together. You guys got this down. Look at the periodic table. Tell me how many valence electrons does carbon have? The answer is yes. Carbon has 4 valence electron. How many more does it need to be 8? It needs 4 more valence electron to be 8. That means how many bonds does it form? That means it makes 4 bonds, because each bond that you form is going to give you another valence electron. So it has 4 valence electron, and what it's going to do is going to form 4 bonds, ends up having 8 valence electron. Okay, nitrogen. Quickly tell me, how many valence electron does it have? It has 5. How many bonds does it make? It makes 3 bonds, so it would end up having 8 valence electron. Okay, pause this video, do the oxygen and fluorine for me. Oxygen has 6, so it needs 2 more to be 8, so it will make 2 bonds, ends up having 8 valence electron. Fluorine has 7 valence electron, it needs only 1 more, so it makes only 1 bond to end up with 8 valence electron. So far so good, beautiful. Now hydrogen has how many valence electron? Hydrogen has only 1. How many bonds would it make? 7? No. Hydrogen has only 1 electron. It can't even afford to make 7 bonds. So hydrogen is an exception. It makes only 1 bond. And hydrogen is happy with 2 valence electron. So hydrogen would only want to make 1 bond. And it would be happy with 2 valence electron in total. And let's look at boron. Boron has how many valence electron? 3. You would think, okay, it has 3 to have 8 valence electron. It would have to make 5 bonds. But boron is another exception. It only makes 3 bonds. And boron is not greedy. Boron is happy with 6 valence electron. Boron is happy with 6 valence electron. These 2 are the exception. Okay? These are the exceptions. Everyone wants to have 8, but hydrogen is happy with 2 and boron is happy with 6. Okay, so let's go over this one more time. Everyone wants to have 8 valence electron, except hydrogen is okay with 2 valence electron and boron is okay with 6 valence electrons. They are not greedy. There is one more exception. Okay, I'm actually going to write it down. There is one more exception. And the other exception is 3rd row down. I'm actually write it down for you. 3rd row down. If you're in the 3rd row down, you can have expanded octet. 3rd row down can have expanded octet. And I'll tell you what that is. But if you're on a 2nd row, you cannot have it. It has to be 3rd row or below to have that. Now, I'm actually going to really make you understand this and not just memorize it as an exception, but understand what this exception is. Remember this? You probably remember this. We did this. Let me do a better job at this. If you remember, we said we have a nucleus, right? We have a nucleus and we have the 1st energy level, we have the 2nd energy level, we have the 3rd energy level, and so on. On the 1st energy level, you had S. 2nd one, you had S and P. 3rd, you had S, P, and D, right? So if you're on a 1st energy level, the maximum electron you can have is only 2. If you're on a 2nd energy level, S has 2, P has 6. The maximum you can have is 8, right? Now, when you come over here, you can have 2, 6, you can have 8, but you also have this empty d orbital. You have this empty d orbital. So you can have a lot more than 8 if you want. So here is the deal. Everyone wants 8 electrons. Except hydrogen wants 2, boron wants 6. But if you have more than 8, it's okay. It's okay to be extra happy but not for the second row. But not for second row atoms on a periodic table. But not for the second row atom. So I'm going to repeat this one more time. So everyone wants to have 8 electrons, except hydrogen wants 2 valence electrons, boron wants 6. Everyone wants 8. But what happens if you end up having more than 8? It's okay. It's okay to be extra happy as long as you're not on the second row of periodic table. So carbon, nitrogen, oxygen, fluorine, those can never have more than 8. But after the second row on the periodic table, it's okay to have 8. They want to have 8. That's the goal. But if you end up having more than 8, that's okay. It's okay to be extra happy as long as you are not on the second row of the periodic table. Okay, great job. Now next time, we have all the background information. We're going to do Lewis structures. We're going to do Lewis structure next time. I'll see you guys then.